Good afternoon. The goal of the lecture of today is to sketch the proof of two important global theorems, precisely the Hopf-Umlauf-Satz and the Jordan curve theorem. Theorem 2.1. So let gamma defined on A B with values in R2 be a simple closed plane curve and let C equal gamma of AB denote its trace. Then we have the first theorem by Hopf, which says that the rotation index of gamma is either 1 or -1. Instead, the theorem by Jordan curve theorem says that R2 minus C, that is P in R2 such that P does not belong to C, is exactly two path connected components one component called the interior is bounded, while the other called the exterior is unbounded. In order to sketch the proof of these two theorems, I need to introduce a more general definition of angle function and one lemma. So, proposition, definition, 2.3. If f from AB with values in S1 is a continuous function with f of A equal to the f of B. Then there exists a continuous angle function theta defined on AB with values in R such that for all t in AB we have f of t equal cosinus of theta t sinus of theta t, and this function is unique up to adding an integer multiple of 2 pi, and I want to define the degree. The degree of f is defined to be the integer one over 2 pi times the difference theta b minus theta a. So this definition here is more general than the one you already know, because here we are not looking at a function f which is the unit speed velocity vector of a curve. Is just a function with values in S1 which is continuous and satisfying this additional condition. So a remark, what I'm going to say follows immediately from the definition of degree. The degree is an integer which represents the number of times the domain of the function f is wrapped counterclockwise around the circle what about the link with the rotation index of a curve? So exercise 1.55, which has been solved by the TA during the problem sessions, implies that the rotation index of a curve, of a closed plane curve, this rotation index appears in the statement of Hopf theorem. Gamma equals the degree of its unit tangent vector. Okay, now I will present the statement of a technical lemma that I will not prove. So I need in the sequel lemma 2.4, which says the following. So let f1, f2 be two functions defined on AB with values in S1. These functions are supposed to be continuous and with f1 of A equal f2 of A and f2 of A equal f2. Sorry, I made a typo. This is B. No, this is correct. Excuse me. This is A. So the typo is here. Sorry, I made a mess here. So the correct statement is f1 of A equal f1 of B and f2 of A equal f2 of B. And the statement of the thesis of the lemma is the following. If f1 and f2 have different degrees, then we have that f1 t0 is the opposite of f2 t0 for some t0 in AB. We will use this lemma in an alternative form. So remark, this lemma says that if the images of f1 and f2 never point in opposite directions, that is this condition here is never satisfied. Then they must have, let's write, then f1 and f2 must have the same degree. So in other terms, if we have one function f1 and you create f2 by slightly deforming f1, if this condition is never satisfied, then you get that f1 and its deformation have the same degree. We will use this fact in the proof of the Hopf theorem and the Jordan theorem. Okay, let's try to give a sketch of the proof of Hopf Umlaufsatz. So suppose that gamma is a plane curve which is simple and closed. Our goal is to prove that the rotation index is 1. Okay, let C denote its trace. Then it is easy to prove that there exists P in C, a point such that C is entirely on one side of the tangent line L to C at P. So let's try to make a picture. Suppose that this is a trace of gamma. Then, for example, you can take this as a point P. Why? Because if you sketch the tangent line to the trace of gamma at P, then the curve is the trace of gamma is entirely on one side of the tangent line L. Okay, up to our reparametrization, we assume that gamma A is P and gamma is parametrized by arc length. Okay, now let's consider the triangle T defined to be the set of points of coordinates T1, T2 such that A is more than T1, is more or equal than T2, is more or equal to B. So if you want to make a picture, the triangle is this. Sorry, I made a mistake. The triangle is this. It is this one and not the one I sketched before because of this inequality. T1 smaller or equal than T2. So this means that the first coordinate is at most equal to the second one, or it is smaller. Okay, let's now construct this function psi, which is defined on this triangle with values in S1. So psi of T1, T2, this is equal to gamma prime T1 if T1 is equal to T2. It is gamma T2 minus gamma T1 divided by its length if T1 is different from T2 and the set T1 T2 is different from AB, and it is equal to minus gamma prime A if the set T1 T2 coincide with AB. So let's erase it here. So this function for most values of its entries is equal to this vector. So for most values of T1, T2, psi is this vector here, and it is a unit vector pointing in the direction from gamma T1 to gamma T2. Okay, now let's introduce alpha 0. This is the parameterization of one of the edges of this triangle, precisely this one. So let's write of the line segment from AA to BB. This is the point AA, and this is the point BB. Now, unfortunately, I have to erase this formula. So let alpha 1 be the parameterization of the line segment from AA to AB followed by the line segment from AB to BB. So in other terms, this line segment here followed by this line segment here. Okay, now I have to erase this part. It is possible to prove that there exists a continuous deformation which sends alpha 0 to alpha 1. So precisely it is possible to interpolate continuously between alpha 0 and alpha 1 by a family of paths that I will call alpha S. They are defined on 0, 1, they take value in t, and the S is a number which varies in 0, 1, and here the word continuously means that the map ST goes to alpha ST is continuous. So you can represent this family of paths, for example, this way. This is an example of interpolation between alpha 0 and alpha 1. Okay, now let's introduce a new function, ds. This is the degree of psi composed with alpha s. Psi composed with alpha s is a map from 0, 1 with values in S1. Okay, it is possible to prove that ds is a constant function on 0, 1. So in particular, this means that t1 is equal to t0. Okay, so if you want to prove this result here, you have to use the lemma 2.4, and using the fact that alpha 0 is a deformation of alpha 1, and this allows you to prove that the degree of psi compose alpha 0 is the same as the degree of psi compose alpha 1, which is exactly the meaning of this identity. Okay, now by definition, let's see what is this 0. The 0 is the degree of psi composed with alpha 0, which is the parameterization of the line segment from AA to BB. So this parameterization is given by, for example, this is just an example, like this, with the first component function equal to the second one. So this means that T0 is the degree of the unit tangent vector of gamma, and we know that this is equal to the rotation index of gamma. Our goal is to prove that the rotation index of gamma is equal to 1. So we have to prove that this 0 is equal to 1, and we will prove that this 0 is equal to 1 using this fact. Okay, now let's observe the parameterization alpha 1. So alpha 1 goes first from AA to AB, which is this point, and then from AB to BB. So since alpha 1 goes from AA to AB, then what is psi compose alpha 1? we can say that this one traces the top half of S1 counterclockwise. Why? Because remember the formula for psi T1 T2 was gamma T2 minus gamma T1 over length of gamma T2 minus gamma T1 gamma T2 minus gamma T1 over its length and something else if T1 different from T2 and T1 T2 different from AB. So you have to imagine what is this vector. Remember that P is gamma A, and precisely you will get that psi T1 T2 is a unit vector having directions given by these vectors here. So these blue vectors are gamma T2 minus gamma T1. But since we divide by its length, you get some vector of unit length. And I cover the top half of S1. Why? Because these vectors here points horizontally or upward. So what about now the horizontal line segment going from AB to BB? So since alpha 1 goes from AB to BB, then psi compose alpha 1 traces the bottom half of S1 counterclockwise. Why this is true? Because this time this vector here points like the vector, the blue vector on the blackboard, but it points in the opposite direction. So this means that I cover S1 always counterclockwise, but I cover the bottom half. I know that this point is difficult to understand, so for this reason I suggest to watch a video which is available in the internet at the address mathematic.com/op/index.html. Okay, so let's try to get a conclusion. So Psi composed with alpha 1 first traces the top half of S1 counterclockwise, and then it traces the bottom half of S1 counterclockwise. So this means that Psi composed alpha 1 makes an entire turn around origin. So this implies that d1, which is the degree of this function, is exactly 1. But d1 coincide with d0, which was the rotation index of my curve. So I prove that the rotation index of gamma, that is d0, equals 1. Please observe that if you work with the opposite orientation of gamma, you will get that d0 is a negative 1. Okay, this is the end of the proof of Hopf-Umlausatz. Now let's try to prove the Jordan curve theorem. Okay, sketch of the proof of the Jordan curve theorem. The proof of this theorem is a bit more complicated than the proof of Hopf-Umlausatz, but let's try anyway to give a sketch. So in order to prove this theorem, I need the notion of tubular neighborhood. Okay, so suppose that as usual gamma is a simple is a simple closed plane curve. Then for small epsilon positive, consider the function phi defined on minus epsilon times AB with values in R2 defined as phi of ST equal gamma T plus S multiplied by the vector R90 V of T, where V of T is the velocity vector of gamma. So let's make a picture. If this is a segment AB, then what we are doing here is to take a neighborhood of this segment, so we get a rectangle whose width is 2 epsilon, and if this is a trace of gamma, the image of phi is this set here. So if we fix the value of the variable t, so if for fix is 0, then S goes to phi is 0S is a parameterization of a small line segment which crosses orthogonally the trace of gamma So for example, if this is T0 and this is gamma T0, then the segment that we are talking about is this one. I want to mention an important fact about this map phi. So we have proposition 2.5. If epsilon positive is small, then phi is injective. In other terms, if I take for example T1, T2, T3 in AB, and they are close to each other, then phi T1s, phi T2s, phi T3s, and of course you can continue. For example, if these are T1, T1, T2, T3, and these are the corresponding segments orthogonal to gamma, to the trace of gamma, then this proposition says that these segments do not intersect each other. So as I already told you, the image of gamma is what we call tubular neighborhood. So the image of phi is called tubular neighborhood. So let's observe the following fact. If the trace of gamma is removed from the tubular neighborhood, then we get two path connected components These are phi of minus epsilon 0 times AB and phi of 0 epsilon times AB, and each of these path connected components is homeomorphic to a rectangle. This is the reason why they are path connected. Okay, let me check how much time I have. Okay. Okay, sketch of the proof. Sketch of the proof of Jordan theorem. So suppose that C is the trace of gamma. Then for any P in R2 minus C, we define a function f of P defined on AB with values in S1 given by the following formula: Fp of T equal gamma of T minus P divided by its length. Now let Wp be the degree of f of P. It's possible to prove that W is a locally constant function so this means it is constant on every path connected component of its domain. Which is R2 minus C. Okay, the idea of the proof, so maybe the goal is show that there are two path connected components of R2 minus C. So how this is done? Idea: show that W takes two different values. Precisely, we will prove that this function can take value 0 and 1 or minus 1. Since this function takes two different values and it is constant on every path connected component of R2 minus C, then there are two path connected components. Okay. So let Q be a point which is sufficiently far from C. So for example, if this is the trace of gamma, you can choose Q to be here. Then what happens to the function f the function f of q defined as gamma t minus q divided by gamma t minus q. So f of q, I forgot to write down t. So fq of t is a function with values in S1. So I can represent S1 here. And gamma t minus q is a vector pointing from q to gamma t. So if, for example, gamma t is this one, then the numerator gamma t minus q is this vector, but since I am dividing by its length, in the end what I get is this vector here. So if I let t vary in AB, I will get the vectors which trace the bottom half S1, bottom half of S1, and so on. So I can say that FQ is not surjective. So what we can say about WQ? WQ is the degree of FQ. So this function, these vectors here, does not make an entire turn of S1. So lemma 2.4 can be used for proving that the degree of this function coincide with the degree of a constant function, and this is 0. Now we have to prove that the function w can take a different value, for example 1. Okay, now the idea for doing this is the following. Consider, for example, this part of the trace of gamma, and here let's choose a zooming window. So I will make a larger picture here. So this is the trace of gamma. I can suppose that up to reparameterization, this point is gamma A, and this point is gamma C. With A is more than C is more than B. And then I choose a pair of points, P1 and P2, this way. P1, P2. We want to prove the following claim. The claim is that W P1 minus W P2 in absolute value is equal to 1. Okay, so what happens to FP1 and FP2? So restricted to AC, which is this interval here, AC. Both FP1 and FP2 are close no, let's say begin with values. So they take the beginning values close to -1, 0, and end with values close to 1, 0. Why? Because for any point on the trace of gamma corresponding to values of the parameter in the range AC, then what is fp1, for example? fp1 of t is gamma t minus p1 over the length of gamma t minus p1. So if you choose this point, then gamma t minus p1 is this vector here, but since we are dividing this vector by its length, you get, for example, this unit vector here, and if you take a point which is instead here, you get a unit vector point this way. What about fp2? fp2 of t, this is gamma t minus p2 over length of gamma t minus p2. So for example, you get this vector here, instead if you work with this point, you get this vector here. You see, this vector is close to this one, and both of them are close to this vector here. This vector is close to this one, and both of them are close to this one. What about the values of this function if t varies in AC? The answer is simple. fp1 covers approximately S1, sorry, the bottom half of S1 counterclockwise, why this is true? If you let t vary between A and C, the yellow unit vector moves this way, and this means that fp1 covers approximately the bottom half of S1 counterclockwise. Instead, if you let t vary in AC, you get that fp2 covers the top half of S1, so I write the fp2 covers approximately the top half of S1 clockwise, because the vector rotates this way. So this means, before going on, I have to mention what happens to these functions for t in CB. I don't make the picture, but it's easy to see that for t in CB, so this means for points of the trace outside this zoom window, we have that fp1t minus fp2t is a length which is more than epsilon. Why this is true? Because these points are very close, and this means that these two vectors are very close to each other and their difference is small. Okay, now the next step is to use lemma 2.4 again to perform a perturbation of fp1, fp2, which do not change the degree. So essentially we will deform fp1, fp2 in the following way. After deformation, we have fp1 a equal fp2 a equal minus 1, 0, fp1c equal fp2c equal 1, 0, and because of this fact, with a small deformation we can get fp1 t equal fp2 t for t in CB. Now the idea is to look at the path fp1t minus fp2t. Okay, so this path, if we use the consideration we made before, it traverses the bottom half of S1 counterclockwise. Why? Because fp1 traces the bottom half of S1 counterclockwise. Then we trace the top half of S1 counterclockwise. Why? Because fp2 traces the top half of S1 clockwise, but here there is a minus sign in front of it. Then it traverses the top half counterclockwise. So I repeat one more time why this is true, because FP1 traverses the bottom half of S1 counterclockwise, and FP2 traverses the top half of S1 clockwise, but here we put a minus sign in front of it, so we have that it traverses the top half of S1 counterclockwise. What is the conclusion of this? The conclusion of this is that this path makes one entire turn, and this means that the degree of FP1 minus FP2 is equal to 1. Because first we traverse the bottom half, then we traverse the top half of S1. So we make an entire turn. But this is degree of FP1 minus degree of FP2, and this is equal to 1. And we finish it because this proves that WP1 minus WP2 is 1. So this means that W takes at least two different values. We proved before that the WQ was 0, and now we prove that the difference between the values of W at P1 and P2 is 1. So this says P1, P2 are in different path connected components Now we have to prove the following claim. These are the only components of R2 minus C. So this means that there are no others. Okay, how this can be done? How this can be done? So suppose again that this is a trace of gamma, and suppose that this is the tubular neighborhood. Okay, let's fix a point, for example, here. Then we want to try to connect P to P1 or P2. How to do this? First, try to connect P to the tubular neighborhood. So for example, you can do this way. And then once you are in the tubular neighborhood, you can extend the path to reach P1 or P2. For example, if P1 is here and P2 is here, you can do this way. In this case, you can reach P1 and not P2 because P2 is located on the other side respect to the trace of gamma. The trace of gamma is marked in white color. So this proves that there are exactly two components. Implies there are exactly two components. Now it remains to prove that one is bounded and the other one is unbounded. How to do this? So let B in R2 be a large ball containing C. So for example, if this is the trace of gamma, then we can take this ball here then clearly one component of R2 minus C contains the complement of B and implies it is unbounded. And this says also that the other component is contained in B, and it is bounded. And this is the end of the proof. Okay, that's all for today. Thank you for your attention.